Hello everyone. First, thanks for the introduction. Please let me introduce our unified TLB and PTC structures named Unified TP. My presentation will follow this outline. Now, let's go to the background. Recent years, data is growing at an exponential rate and is not going to slow down in the short time. According to the report, the amount of data has increased 44 times from 2009 to 2020. As a result, the storage and memory capacity increase and applications with large dataset emerge. Therefore, the pressure on virtual memory performance is dramatically increasing. Previous work focused on two ways to improve the performance of adjust translation. The first is to decrease the TLB miss rate. For example, huge pages are used to expand the translation coverage of TLBs. The second focuses on reducing the TLB mishandling latency. For example, page table cache are used to store upper-level page table entries to reduce low-latency page table walks. These methods are used exclusively either for TLBs or PTCs. We believe that the structural separation between TLBs and PTCs limits the acceleration of adjust translation. Now, let me show you the motivation of our work. To give a better understanding, we divide the workloads into two types based on their memory access behaviors. The data in the first type of applications tend to have a long reuse distance, which means that when a data item is accessed again, the translation record for that data item has been deleted from TLBs. In our experiments, the results showed that about 5% pages contribute 50% of the total TLB misses for full graph workloads. In this case, if we can shrink the PTC space and provide more space for TLB, it can reduce memory access overhead. The second type of applications, such as time serial databases, is characterized by sequential access of memory pages. That is to say, there are almost no repeat requests, so the utilization of TLBs is very low. On the contrary, PTCs have a high hit rate because of the good locality. In this case, we can delete useless TLB entries and expand PTC space to reduce memory access overhead. Therefore, the physical and logical separations of TLB and PTC structures renders it impossible to dynamically adjust their sizes according to the workloads. In order to solve this problem, we propose a unified TLB and PTC structure. As shown in the left picture, we combine TLB and PTC into a single structure. In our design, for TLB entries, they are similar to those in the baseline system. And for PTC entries, they adopt the same indexing scheme as TLB entries to make it easier to design and implement in hardware. As shown in the right picture, the tag of a PTC entry is a portion of virtual page number. Since baseline system enables the respective circuitries of TLBs and PTCs, searching entries can be executed in parallel. In contrast, searching entries in unified TP should be executed in a sequential order if there is only one circuitry. Therefore, we propose a parallel search scheme. The basic idea is to provide equal circuitries as baseline system. When receiving a memory request, each circuitry checks one of the corresponding entry among TLB and level 2 to level 4 entries. According to the check result, replacement information should be updated. In this case, multiple circuitries hits may incur data consistency issues. Therefore, among the hit entries, we update the replacement information of the entry with the longest tag to make sure that only one entry will be updated once a time. According to the parallel search, we also need to modify the LRU algorithm. When insert missing entries into unified TP, the insert order is from the upper to lower level. This is because hits in lower level require fewer memory accesses than those in upper levels. Then, LRU algorithm can evict entries according to the workloads. Next, I will show you the experimental data. We implemented the unified TP on a trace-based simulator and used pin-binary instrumentation tool to generate the memory access trace. The data size of our evaluation includes 2 kernels from PASIC Suite, Graph 500, and 3 workloads of Graph Big Suite. The detailed setting of system configuration is shown in the table. We evaluate the number of TLB misses and memory accesses of unified TP and baseline system. The experiment results show that unified TP reduces TLB misses rate and memory accesses by 35.69% and 36.93% on average for all benchmarks respectively. This picture shows the execution time based on the latencies in the table of experiment setup. The results show that unified TP achieves performance improvements by 11.12% on average for all benchmarks. The contributions of our work are as follows. First, we proposed unified TP to dynamically adjust their entries based on the assigned characteristics of workloads. Second, we designed a parallel search scheme to improve the search performance. And finally, we proposed a modified LRU replacement algorithm to help identify the code TLB and PTC entries. Thank you for listening.